In this video, we're going to discuss the concept of a crystal field stabilization energy. So that's the original, that's the name that we usually use when we're talking about crystal field theory. But what we're also going to refer to, for reasons that will make sense later in the class, as a ligand field stabilization energy, or LFSE. Okay, as we talked about in the last video, when we look at the atomic d orbitals, we have 5 degenerate orbitals, and these are not split. However, when we apply a geometry, an octahedral geometry, or we apply ligands that coordinate to the metal with an octahedral geometry, we get what's called an octahedral crystal field, and this results in splitting of these 5 degenerate orbitals into 2 sets of orbitals, one that is lower in energy and is triply degenerate, which we refer to as T2G, and then another set of orbitals that is doubly degenerate, and we refer to as EG, the EG set of orbitals. Okay, in this, right, let's take, for example, if we want to figure out the electron configuration in an octahedral ligand field, we want to be able to, we follow our normal principles of the Aufbau principle, Hund's rule, and Pauli exclusion principle, and we see the T2G orbital is lower in energy. So let's take an example. Let's start with vanadium-2, okay? The electron configuration is going to be 3d3. So we have three electrons in the d orbital, and so when we fill this, right, obviously we're going to fill the lower energy orbitals first, and so and then we're going to avoid pairing to avoid Coulombic repulsion within the orbital, and then these spins are going to align, which will satisfy the rule that we try to achieve the highest spin, okay? And so when we do that, that's great. This is the electron configuration we expect. And so for V2 plus, if we just think about the T2G and the EG set, what we would say is we have T2G to the third, EG 0, okay? Now, what happens, right, if we go to chromium 2? Now this has a D4 electron configuration, and so we have an additional electron. Now the question becomes, right, how do we fill this? So the gap, as we discussed in the last video, between the T2G and the EG set, we refer to as delta O, okay? And that's the splitting between the energy difference between the higher energy EG set of orbitals and the lower energy T2G set of orbitals, okay? And we can also, if we compare this, right, to the original energy of the atomic orbitals, right, what we see is that the energy here, from here to the original energy of the atomic orbitals, which we refer to as the Berry center, is going to be equal to a stabilization of -2/5 delta naught, or delta O, excuse me, okay? Whereas from the Berry center to the EG orbitals, this is going to be a destabilization of 3/5 delta O, okay? And so what we can then say, right, is if we're still looking at the vanadium-2 electron configuration, is that compared to the atomic d orbitals, where if we had vanadium-2, all the electrons, right, that would be the electron configuration. They'd be in the 3d orbitals, which are all degenerate, okay, for the 5 of them. Compared to this energy, right, in the octahedral crystal field, right, we have stabilized the electron configuration by 3 times -2/5 delta O, which is going to be equal to -6/5 times delta O. Okay, so we've stabilized that, we just stabilized the energy in the octahedral crystal field by this much, by -6/5 times the energy of delta O. Okay, now what do we do when we come back to this chromium 2 plus? So we have sort of a conundrum here, right? So either the electron, that fourth electron, can end up in the T2G state, but now there's Coulombic repulsion because we've added that electron into an already filled orbital. The alternative is that the electron goes into its own orbital in the higher, but in its own orbital, but it's in the higher energy EG state. Okay, and so these two scenarios result in this case, we call this the high spin state. Whereas in the other scenario, we have what's referred to as the low spin state. Okay, where this has a spin of 4 times 1/2 equals 2, and this has a spin of 3 times 1/2 plus -1/2 is equal to 1. Okay, so the reason we call this the high spin state and the low spin state is because this spin state has the higher value of spin versus this has the lower value of spin. Now what dictates this? Okay, so in the high spin state, we have to consider, right, what we consider is the competition between the energy of the increased energy of going from the T2G to the EG state, right, which is delta O, and compare it to the energy of pairing a second electron into an already filled orbital, okay, which we refer to as P, okay? So when delta naught is less than P, right, where P is the pairing energy, right, what we end up with is the high spin state, okay? Meanwhile, if we have delta O is greater than P, then it is more favorable to put that to sort of take the penalty of pairing the electron into that filled orbital, and what we end up with is the low spin state here. Okay, and this is what influences, right? It's this competition between the difference in the energy between the T2G and the EG state, the delta, with the pairing energy, which is the repulsive effect between the electrons in a filled orbital that determines whether the compound prefers to be in the high spin or the low spin state.